Hi, my name is Ido, and I'll be presenting my work on isolating vocals from music using convolutional neural network model. And I've been following the excellent blog post um, suggested by Koretsky. And the main idea that he presented was representing the data, the music track as a spectrogram in the frequency domain, and then taking just a single time frame at a time and predicting the vocal activity in that time frame using the time frames, the neighbor time frames that are surrounding the target time frame. So the spectrogram looks like an image. So it follows naturally to use a model that is a convolutional neural network because those models have shown great success on image data. So my work, my main contribution is an ablation study on the concepts suggested by the Koretsky blog post, and that's it. That's the main work. So without further ado, I'll go straight into the ablation study, the experiments. So I studied three different aspects of the method Koretsky suggested. So the first is the contextual window. I wondered if we indeed need in our features timeframes both from the past and the future, like timeframes that are previous to the target timeframe, and also timeframes which follow the target timeframe. And I wondered, can we actually get by with a causal model that contains only timeframes from the past, which is obviously useful for a streaming model. The second aspect that I've studied is the main idea of the blog post, which is using binary mask prediction, like predicting for every frequency if there is or there is not vocal activity in that frequency. And instead, I tried using a simple regression model that predicts for every frequency what is the amplitude of the vocal activity in that frequency, or zero if there is no vocal activity in that frequency. And the third concept that I've studied is whether the mel scale perceptive feature space is helpful for this problem, or can we get by simply using short time Fourier transform like the raw frequency domain. So let's see the main table that summarizes our results. So the results, we can see the four models in the four rows of this table. And the metric that we measured is the mean squared error in the time domain, right? The simple reconstruction of the waveform. We took the reconstructed waveform and we took the original waveform of the vocal activity and we compared them one sample at a time, the entire time domain, and we averaged over the entire test set. Just to mention that the train set and the test set that we use were faults of the MuseDB 18 dataset, which contains hundreds of hours of recorded music and the corresponding vocal activity for every music track. So we can see in the first line that of the table that indeed, as expected, the causal model did worse than the binary mask prediction model that used both features from the past and features from the future. So that's expected. What's not expected is what we see at the third row of this table, where the regression model did better than the binary mask prediction, and not as Koretsky described in the blog post. The simple regression approach with exactly the same model architecture did better than binary mask prediction. And the most surprising thing is that we don't need Mel scales because we tried a model that does simple raw short time Fourier transform, and we got the best performance of all four models. And you can hear in the accompanying audio samples to these presentations, you can hear that for yourself. That the best quality was for the fourth model. And that's it for our work. And I'll want to share two learning experiences, the main learning experiences that I tackled in this work. So the first challenge, the first learning experience was that you must eyeball and see your labels before you start training expensive models, because we did a mistake and defined for the binary mask prediction, defined that y equals to 1, the target equals to 1 for any frequency that has any vocal activity, like amplitude that is higher than 0. That proved to be much too sensitive and much too noisy, and it's much better to set a threshold of epsilon, like I don't know, the vocal frequency is higher than 0.1, and that's a better definition of a frequency with vocal activity. Because many frequencies has very little noise, and there are false positives. Also, the second learning experience are the many subtle differences between the platform that we chose, which was JAX, from the platform that Koretsky chose, which was Keras. So there are many similar things, but there are subtle differences. We had to use JAX because we wanted to make use of the TPU, the pufferfish platform that we had at our disposal. So JAX is excellent in using parallel computing over the JAX, the TPU platform. But there are certain differences, certain quirks, like a different default max pool stride, and a requirement to do expand dimensions before applying any convolutions, like little things that can beat you if you don't pay attention and just copy as is from Keras. So that was the second learning experience, and that's it. And thank you for this project and opportunity, and we hope that you enjoy the audio samples that we produced. That's it.